Determining the correct number of conductors allowed in a conduit is crucial for electrical installations to prevent overheating and ensure safety. A formula can be used as a guideline, but always consult the National Electrical Code, or NEC, for specific requirements. The basic formula is number of conductors equals conduit volume minus wire volume times number of wires, all divided by free space. Let's break down each variable in this formula. Firstly, conduit volume refers to the internal volume of the conduit, typically measured in cubic inches. This value depends on the conduit size and type. You can find this information in manufacturer specifications or relevant tables in the NEC. Secondly, wire volume represents the volume occupied by a single conductor, also measured in cubic inches. This value depends on the wire's gauge, insulation type, and whether it is a solid or stranded conductor. Again, this data can be found in wire manufacturer specifications or NEC tables. Thirdly, number of wires is simply the total number of conductors you intend to run within the conduit. This is the variable you'll often be solving for. Fourthly, free space refers to the unoccupied space within the conduit, which is essential for heat dissipation. Overcrowding a conduit can lead to overheating, insulation damage, and potential fire hazards. Typically, the NEC specifies a maximum conduit fill percentage, which translates to a minimum free space requirement. A common practice is to reserve 40% of the conduit volume as free space for heat dissipation. This can be calculated by multiplying the conduit volume by 0.40. To illustrate how this formula works, let's consider an example. Suppose you're using a 1-inch conduit with a volume of 0.64 cubic inches. You plan to use 12 American wire gauge, or UG, THHN wires, each having a volume of 0.24 cubic inches. To determine the maximum number of 12 AWG THHN wires you can safely run in this conduit, follow these steps. Firstly, identify the known values. Conduit volume equals 0.64 cubic inches. Wire volume equals 0.24 cubic inches. Free space equals 0.40 times 0.64, which equals 0.256 cubic inches. Number of wires is the unknown variable we want to find. Secondly, plug the known values into the formula. Number of conductors equals 0.64 minus 0.24 times number of wires, all divided by 0.256. Thirdly, solve for the number of conductors. This involves some algebraic manipulation. Multiplying both sides of the equation by 0.256, we get 0.256 times number of conductors equals 0.64 minus 0.24 times number of wires. Rearranging the equation, we get 0.256 times number of conductors plus 0.24 times number of wires equals 0.64. Combining the terms with number of wires, we get number of conductors times the quantity 0.256 plus 0.24 equals 0.64. Dividing both sides by the quantity 0.256 plus 0.24, we get number of conductors equals 0.64 divided by 0.2584, which is approximately 2.476. Therefore, the calculation is number of conductors is approximately equal to 2.476. Since you can't have a fraction of a wire, you would round down to the nearest whole number. In this example, the calculated number of conductors is around 2.476. However, in practice, you would typically round down to ensure compliance with safety standards and code requirements. So, in this scenario, you could safely run two 12 AWG THHN wires in the 1-inch conduit. It is important to note that this formula provides a theoretical maximum. Always consult the NEC and local electrical codes for specific requirements and earthing factors, which may further limit the number of conductors allowed. For example, NEC Table 310.15 B3 addresses adjustment factors for more than 3 current carrying conductors in a raceway or cable. The allowable ampacity of conductors shall be reduced as shown in the table. Number of current carrying conductors 4 through 6, the percent of ampacity is 80%. Number of current carrying conductors 7 through 9, the percent of ampacity is 70%. Number of current carrying conductors 10 through 20, the percent of ampacity is 50%. Number of current carrying conductors 21 through 30, the percent of ampacity is 45%. Number of current carrying conductors 31 through 40, the percent of ampacity is 40%. Number of current carrying conductors 41 and above, the percent of ampacity is 35%. Another important consideration is the type of insulation used on the conductors. Different insulation types have different temperature ratings, which affect the allowable ampacity of the conductors. THHN, THWN, and XHHW are common insulation types, each with its own specifications. Always refer to the NEC tables to determine the appropriate ampacity for the conductor size and insulation type. Furthermore, the presence of other heat-generating equipment near the conduit can also affect the allowable number of conductors. If the conduit is exposed to direct sunlight or high ambient temperatures, the conductors may need to be deaerated to prevent overheating. In addition to the formula and NEC guidelines, it's crucial to consider practical factors when determining conduit fill. Avoid overcrowding conduits, as this can make it difficult to pull wires, increasing the risk of damage during installation. Ensure that the conduit is properly sized to accommodate future expansion or changes in the electrical system. When presenting this information, consider the following points. Firstly, emphasize the importance of proper conduit fill to prevent overheating and damage to wires. Overcrowding a conduit can lead to reduced airflow, increased heat buildup, and premature failure of the insulation. Secondly, clearly define the variables in the formula, explaining how they are calculated and where to find the necessary information. Use diagrams and visual aids to illustrate the concepts and make them easier to understand. Thirdly, walk through the example calculation step by step, explaining each step and the reasoning behind it. Encourage questions and provide additional examples to reinforce the concepts. Fourthly, highlight the importance of consulting the NEC and local electrical codes for specific requirements and deterring factors. Emphasize that the formula is a guideline, and actual calculations should be based on the specific job requirements and code compliance. Finally, discuss practical considerations such as ease of installation, future expansion, and the impact of environmental factors on conductor ampacity. By covering these points, you can provide a comprehensive explanation of how to determine the number of conductors allowed in a conduit. Remember, safety and code compliance are paramount in electrical installations. Always double-check your calculations and consult with a qualified electrician if you have any doubts. Understanding conduit fill calculations is a fundamental skill for any electrician. It ensures safe and efficient electrical systems by preventing overheating and potential hazards. The NEC provides detailed guidelines and tables for determining the appropriate number of conductors in various conduit types. These guidelines take into account factors such as wire size, insulation type, ambient temperature, and the number of current carrying conductors in the raceway. The formula we discussed provides a simplified approach to understanding the basic principles behind conduit fill calculations. However, it's essential to always refer to the NEC for accurate and up-to-date information. The NEC tables provide specific values for conduit fill based on different wire sizes and types. For example, NEC Table 310.16 provides the allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius in ampacity correction and adjustment factors. This table lists the maximum allowable current for different conductor sizes and insulation types in various conditions. In addition to ampacity, the NEC also specifies the maximum allowable percentage fill for different types of conduits. This is typically expressed as a percentage of the conduit's cross-sectional area. For example, NEC section 344.22 provides the allowable conduit fill for different types of conduits, such as rigid metal conduit, or RMC, intermediate metal conduit, or IMC, and electrical metallic tubing, or IMT. The allowable fill percentage varies depending on the number of conductors in the conduit. For one conductor, the maximum fill is 53%. For two conductors, the maximum fill is 31%. For three or more conductors, the maximum fill is 40%. These fill percentages ensure that there is adequate space within the conduit for heat dissipation and to facilitate wire pulling. Overfilling a conduit can make it difficult to pull wires, potentially damaging the insulation and reducing the conductor's ampacity. It can also lead to overheating and premature failure of the electrical system. When performing conduit fill calculations, it's important to consider all the factors that can affect the conductor's ampacity and the conduit's fill capacity. This includes the ambient temperature, the number of current-carrying conductors in the raceway, and the type of insulation used on the conductors. In addition to the NEC, local electrical codes may also have specific requirements for conduit fill. It's essential to consult these local codes to ensure compliance with all applicable regulations. Proper conduit fill calculations are essential for ensuring the safe and reliable operation of electrical systems. By following the guidelines in the NEC and local electrical codes, you can prevent overheating, reduce the risk of electrical fires, and extend the lifespan of your electrical equipment. The information in NEC Chapter 9 contains tables and examples for conduit and tubing fill calculations. Table 1 provides the percent area of conduit and tubing for conductors and cables. Table 4 provides the dimensions and percent area of conduit and tubing. Table 5 provides dimensions of insulated conductors and fixture wires. Table 5 provides compact aluminum building wire dimensions. Table 8 provides conductor properties. Table 9 provides AC resistance and reactance for 600-volt cables, 3-phase, 75 degrees Celsius, 3 single conductors in a conduit. Table 11 provides examples of conduit and tubing fill calculations using Table 1 and Table 5. Table 11b provides examples of conduit and tubing fill calculations using Table 4 and Table 5. When calculating the number of conductors permitted in a conduit or tubing, all conductors in the same raceway shall be of the same insulation type and constructional materials such as copper, aluminum, or copper-clad aluminum. The sum of the cross-sectional areas of the insulated conductors shall not exceed the percentage of the interior cross-sectional area of the conduit or tubing as shown in Table 1 of Chapter 9 of the NEC. When calculating conduit fill, remember that the cross-sectional area of the conductors includes the insulation. The dimensions of insulated conductors are provided in NEC Table 5. It is important to use the correct dimensions for the specific type of conductor being used. For example, THHN conductors have different dimensions than THWN conductors. Furthermore, the NEC requires that all conductors in a raceway be of the same insulation type. This is to ensure that the conductors have compatible temperature ratings and to prevent chemical reactions between different insulation materials. In addition to the conductor dimensions and insulation type, it is also important to consider the conduit type when calculating conduit fill. Different types of conduits have different internal diameters, which affects the available space for conductors. NEC Table 4 provides the dimensions of different types of conduits, including rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and flexible metal conduit. It is important to use the correct dimensions for the specific type of conduit being used. When calculating conduit fill, it is also important to consider any fittings or accessories that may be installed in the raceway. These fittings can reduce the available space for conductors and must be taken into account when determining the maximum number of conductors permitted in the conduit. For example, conduit bodies, such as LB fittings and T fittings, can significantly reduce the available space for conductors. The NEC provides specific rules for calculating the fill capacity of conduit bodies. In addition to the NEC requirements, local codes and regulations may also impose additional restrictions on conduit fill. It is important to consult with local authorities to ensure compliance with all applicable requirements. Proper conduit fill is essential for ensuring the safe and reliable operation of electrical systems. Overfilling a conduit can lead to overheating, insulation damage, and premature failure of the electrical system. It can also make it difficult to pull wires, increasing the risk of damage during installation. By following the guidelines in the NEC and local codes, you can ensure that your electrical installations are safe, efficient, and compliant with all applicable regulations. In summary, determining the number of conductors allowed in a conduit involves a combination of calculations, code references, and practical considerations. While the formula presented provides a basic understanding of the principles involved, it is crucial to consult the NEC and local electrical codes for specific requirements and guidelines. Remember to consider factors such as wire size, insulation type, ambient temperature, conduit type, and the presence of fittings or accessories. By following these guidelines, you can ensure that your electrical installations are safe, efficient, and compliant with all applicable regulations. Always prioritize safety and consult with a qualified electrician if you have any doubts or questions.